Hi everyone, today I'm going to present our recent work accepted by ICCV 2023, Dynamic Perceiver for Efficient Visual Recognition. In the deep learning era, especially in the upcoming large model era, the high computational cost of deep networks still hinders them from being applied in many resource-constrained scenarios. As a result, people are paying more attention to improving the inference efficiency of deep networks. Although extensive efforts have been made in this direction, such as model pruning and weight quantization, intrinsic inefficiency still exists in the commonly used networks, including CNNs and vision transformers. Such inefficiency comes from the static inference paradigm. In other words, static models process different inputs with equal computation. This behavior overlooks the complexity variance of different samples, leading to considerable redundant computation on those easy samples. To address this, an effective solution is dynamic inference, which means that the computation can be adaptively adjusted conditioned on each input sample. For example, a dynamic model may allocate less computation on those easy samples at test time. Early exiting is a representative approach to achieving input-dependent computation. Specifically, to obtain the prediction of each sample, a traditional network needs to execute all its layers sequentially, and the prediction is obtained at the end of the model. In contrast, if we have a dynamic model with multiple exits located at different depths, we can have a prediction result at each exit. Once the prediction confidence at an early exit satisfies some criterion, the forward propagation could be terminated, and the execution of deeper layers will be saved. In this way, we allow the model to process easy samples with a shadow subnetwork, and only hard samples will be propagated to deep layers. However, designing a model that can perform dynamic early exiting is a challenging task. Researchers have found that if we directly append intermediate classifiers in a visual backbone like ResNet, the performance of the final exit will downgrade significantly, and the classifiers would interfere with each other. To solve this problem, some multi-scale structures have been proposed. Despite their effectiveness, such specially designed architectures are hard to generalize across different backbones. Ideally, we hope to empower any backbone with the ability of early exiting instead of designing a specific architecture from scratch. To this end, our goal is designing a general framework for dynamic early exiting. This framework should be compatible with any visual backbones. Given that directly adding classifiers in a backbone is suboptimal, our solution is the proposed dynamic perceiver, a two-branch architecture which explicitly decouples feature extraction and early classification. Specifically, the first branch is named feature branch, which can be selected as any visual backbone. The second branch is named classification branch. Its input is a latent code. This latent code is a learnable token sequence, which is specially used to encode high-level semantics. We build interaction between these two branches via cross-attention layers. Finally, multiple early classifiers are appended in the classification branch. Later, we will use an ablation study to show that such decoupling is suitable for dynamic early exiting. Here is a detailed architecture of our dynamic perceiver. It is generally composed of 4 stages. At the beginning of each stage, a cross-attention layer is used to distill the input information into the latent code. After that, the two branches execute their computation blocks respectively. At the end of each stage, a reversed cross-attention layer feeds the semantic information back into the feature branch. Moreover, we build token mixers between every 2 stages of the classification branch to mix information along the token and channel dimensions respectively. We use this ablation study to show the effectiveness of our two-branch design. First, we directly add an early classifier in a CNN and a vision transformer with classification token. It can be seen that the performance of their final exits drops significantly. Next, we add an early classifier in the feature branch of our dynamic perceiver. The final exit's performance slightly drops. Finally, when we add the early classifier in the classification branch, we are glad to see that the final performance is even improved. These results demonstrate that our classification branch is suitable to construct intermediate classifiers. It not only improves the final performance of the model, but also enables dynamic early exiting during inference. Here are our main results. In each subfigure, the x-axis is the computational cost, and the y-axis is the accuracy. We first conduct experiments on ImageNet classification with multiple visual backbones, including ResNet, RegNet, and MobileNet v3. The results show that our dynamic perceiver outperforms various static baselines. Moreover, it also achieves a better trade-off between accuracy and efficiency than other dynamic early exiting approaches. Finally, we validate its effectiveness on the video classification task by replacing the ResNet 50 backbone with our dynamic perceiver in the TSM framework. Our dynamic perceiver also demonstrates superior performance on different hardware platforms, including an edge device TX2, a desktop CPU, and an A100 GPU. Here we visualize the easy and hard samples selected by different exits of our model. It can be seen that the easy samples usually contain canonical features, while the hard samples could contain some non-canonical features. We summarize some takeaway messages here. Dynamic early exiting is an effective approach to improving the inference efficiency of deep networks. However, traditional early exiting models are hard to generalize across different backbones. Our two-branch design explicitly decouples feature extraction and early classification, which is suitable for dynamic early exiting. The proposed dynamic perceiver can be built on top of any visual backbones, showing superior trade-off between accuracy and efficiency on visual recognition tasks. Thanks for your time. For more details, please refer to our paper and code.